Hi, and welcome back to the helper videos for exponential functions, either for helping folks doing do-overs on the exponential functions test or preparing for future exponential functions tests. These problems are based on similar problems from the April 2019 exponential functions test. And right now I'm going to deal with problem 4, which on the original test involved the depreciation of a chicken car. In this case, we're going to consider an electric automatic banana peeler a real thing one can buy. It really exists as a thing. So, some time ago, you bought an electric automatic banana peeler. It has been depreciating in value for some time at an annual rate of 46%. Now, in 2019, it is valued at $1,200, and you originally bought it for $5,000. Round all answers to the nearest tenth. So, before we go anywhere, we need to set up a basic equation, and while we're setting up that equation, we need to choose our initial value. I think if we set up 2019 as our initial value year, we can pick 1,200 as our initial value, and this 5,000 will be sometime in the past. We can work things out that way. So, that's what I'm going to do. You could set it up as if the time in the past was our initial value, but you wouldn't know how many years until 2019, so that could get a little tricky. It's still doable, but I'm going to pick 1,200 as our initial value, which means 2019 is our 0 year. So y is going to equal, we're going to have our initial value, which will be our principal, times 1, and then we're going to say minus, because it's depreciation, 0.46, which is our rate, over our number of compounding events, and that's going to be raised to the number of compounding events times x. X will be time. Remember, this is just basically y equals p times 1 plus r over n raised to the nt power, where t is just time and we're using x for time here. Okay, so in our first version of this, we need to figure out how long we've had it. So we're going to use annual compounding, and that means that the number of compounding events in a year is 1. It's an annual rate of 46% of depreciation, and that's happening just once a year. So that'll be also 1 times time. The 0.46 will be divided by 1. So we're going to use this basic equation. We're going to say y equals, well, set our initial value, as I said, at 1,200 times 1 minus 0.46 divided by 1, which means we really just say that. We don't even need to divide by 1, and that's going to be raised to the x power. Right? And then what we need to do is we need to figure out when this function, how long ago, how many x values in the negative territory we go till we find this function intersecting with y equals 5,000. That's when the value of the banana peeler was $5,000. That'll be in the past because this is depreciating. And then we'll have to work out what that number plus 2019 is. It'll be a negative number plus 2019, which will give us an earlier time. So let's go over to Desmos, and we'll say y equals 1,200 times 1 minus 0.46. I'm going to go ahead and write over 1 just to remind you that we are compounding, raised to the 1x power. Okay, and then we will say y equals 5,000, and I'm going to change how my whole scale is and zoom out again. I'm going to zoom this way. I could go to the little wrench and do it that way, but I'm going to do it this way because it'll be quicker for the video. And here is when the function equals 5,000. We click on that intersection point, and that is 2.316 years ago. not that far ago. So we're going to say, okay, we say 2019 plus negative 2.136, and we get 2016.864. We round that to 2016.9. So we bought this thing in 2016.9, which is sometime in November, sometime in September, probably of 2016. So we can say bought it sometime in September of 2016. I say September because 0.9, there's 12 months, but 9/10 is approximately sometime in that 9th month of 2016. You could have gotten away with saying 2016.9, and I would accept that, but you can take it that extra step. So it was bought probably sometime in 2016 in September. Okay, what if it was compounding monthly? We're going to use the same function, only we got to deal with the monthly compounding. So go down here, and instead of that, we're going to say that's going to be divided by 12. We're breaking that negative 0.46 into 12 parts, and then we're going to make it 12x because we're in every year, x is years, and every year we're going to have 12 of those compounding events. So we'll plot that, and we will see where that intersects with y equals 5,000. So let's go back into Desmos, and we say y equals 1,200 times 1 minus 0.46 divided by 12 raised to the 12x power. And now I'm going to turn the other one off to make it a little less confusing. We see where that intersects. It intersects 3.043. So we're going to take the same thing, copy that over here, and replace that with negative 3.043. 043, and we get 2015.9. Actually, we'd round that to 2016. So right at the beginning of 2016, we would have bought it if it was compounding monthly. So 2016 is 0.0 is the rounded number. Bought right at the start of 2016. And that's the information you got there. Now, if it was continuous, now continuous is going to be a different equation. Continuous requires us to use E. So we'll say y equals 1,200 as our initial value. Y equals 1,200 as our initial value times E. Now that's going to be raised to the negative 0.46 x power. Because it's depreciation, we make that rate negative. There's no 1 involved. The 1 is already taken care of by Euler's number there. So we'll go in here. We're going to make that one disappear. We'll plot that y equals 1,200 e raised to the negative 0.46 x power. And let's see where that intersects with 5,000. In this case, 3.102. So 3.102, copy that, change that to 102, and sometime in late 2015, so 2015.9, again, so we're way late 2015, and I'm going to revise my answer for this one instead of saying September, because 9/10 of the year is probably not September. We can probably say December of 2016. But back here, we'll say right at the end of 2015, maybe December, maybe November. Okay, late 2015, and we'll get rid of that. We're superscripting there. And we are out of time.